In general, probability is defined as the following. A probability is simply the ratio what are called successful outcomes over total. Outcomes. Successful outcomes being things we're going to look at. It's going to vary by situation. So for example, a successful outcome when I roll, say, a die, would change depending on what I want to come up. So like in the case for the homework roll, a successful outcome might be rolling a 5 for us. You might consider that a success. I want to roll a 5. So what's the probability of rolling a 5? 1. There's 1 5 and there's 6 faces. 6 total faces in the die, there's only 1 5. Versus what's the probability that your homework gets checked based on our die rolling system?
3 out of 6.
There's 3 numbers that could come up. And there's 6 total possibilities, so it would be 3 out of 6, or 1/2 would be the ratio, would be the probability in this what's called this discrete case. Okay? Geometric probabilities are taking this idea and extending it to more general cases, to what are called continuous cases. In general, our geometric probability is going to be the ratio of I don't want to define this. We'll do it in a 2-dimensional case. Yeah, kind of the thing that we've been. That's not much better. Thing that we've been talking about this whole chapter. Over total area. So common places we see like geometric probability. A really common examples are like targets. Like if you're like playing darts. Like you've got a circle that's divided up into certain categories, and we can determine if something landing on a dartboard is totally random, what's the probability that lands at, say, like the bullseye? Well, there's not we can't define there's not a discrete amount of, say, points that are in there. Like a plane has an infinite number of points. But we can look at area. We can compare the area of a part compared to the area of the whole. This same applies in we'll look at what are called one-dimensional case, which is below. We just look at a number line. We can compare the lengths as well as a continuous or called geometric case. So, for example, we're going to find a probability that if I choose a point at random on segment PQ, that it lands in one of these given segments. So it's the idea of comparing a successful outcome, like something that I'm looking for, that I want to happen, versus all the possibilities, the total possibility. So in a one-dimensional case here, I can compare lengths. So, for example, how long is the successful length in our first one? What's the length of segment RT? RT has a length of 1. Compared to if a point that I choose could fall anywhere at random on segment PQ, well, here's the total length. What's the total length of segment PQ? 10. So if I pick any point at random on segment PQ, what's the probability that it lands on segment RT? 1 out of 10. The successful length RT over the total possibilities, which is 10. Our probability is this ratio, 1 over 10. How about instead on TS? Let's look at the length of TS. What's the probability that I pick a point at random between PQ and it lands somewhere in that segment? 1/2. So we compare the length here, 1, 2, 3, 4, 5. Successful length of TS, so the success is 5. Total length of 10, exactly breadth. 5/10 reduces to 1/2. Let's continue the idea. Let's find, on your own, quickly jot down the probability of landing on PT and the probability of landing on RQ. PT has a length of, from P to T is a length of 1, 2, 3, 4. Probability of landing on PT is 2 out of 5. Probably landing on RQ is 1, 2, 3, 4, 5, 6, 7 out of 10. Okay. Probabilities are, in general, we'll leave them as fractions a lot of times. More commonly, though, we'll see them as percentages. So we'll, in general, write our probabilities as a percentage. Namely, that would put RT at 10%, 50%, 40%, and 70%. I guess before we get too much farther, just in general, if we're not familiar 100% with probabilities, probabilities are always expressed as a number between 0 and 1, with 0 being impossible to achieve and 1 being 100% certain to achieve. For example, the probability of me giving you an assignment tonight is at 100%.
No, there's other factors. The school.
The probability.
Explode.
The probability of. I was going to give 0%.
They're going to college.
Yeah, the probability of me giving you English homework, is a good example, is 0%. I'm not going to give you English homework.
No.
I have about a 40% chance of making an assignment. I want to model my situation in this, like, what's called a continuous case. Like, I don't know, like, I could have arrived at any, like, millisecond or nanosecond in between. It's a different possibility. I can't just label all the possible times. But I can compare their relative lengths. So if I turn this situation into, say, into like a number line, if I can find some ratios of some good and bad times, I'm going to be pretty much good to go. Okay. This is what's called a one-dimensional case because it's just on a number line. We can do the same thing with areas. So, like as I said, like a dartboard or a target's a pretty common two-dimensional case here. So, if a dart game here use a target with concentric circles of radii 5 and 8 inches. If the dart is equally likely to land on any part of the target, what's the probability that I'll earn 20 points? So if I just close my eyes and throw at random, and I know I'm going to hit the target close enough, I'll hit it, but I don't know where. What's the probability that I'm going to get in the 20-point bullseye? Oh, I'm missing a number there, huh? 5, 8, and there's supposed to be a 12 in here as well. So it's saying we have a 5, 8, and 12 inches. I missed the 12, so that's what the diagram is a little bit. I have concentric circles, and I know the first has got the following radii. I'm going to throw a dart at random. I'm going to calculate the probability it's going to land somewhere. I know it's going to land on the target somewhere. So I'm going to be in this circle somewhere. I just don't know where it's going to land. It's kind of fall around. What's the probability to get a bullseye? Well, this is a geometric case. This is a two-dimensional case. I got length and width here. Well, I could compare, just like I compared the relative length of a success to a length of the total possibilities, I can do the same thing, but now in an area case. So let's find the area of my successful shot. In this case, what's the area? How much area is a 20-point shot? And compare that to the area of the entire dartboard. So in general, I'm going to compare the area of the success compared to the total area. Our success we're defining to be earning a 20-point shot, or the bullseye. So what's the area of the bullseye in this case? Well, it's a circle.
2.5 squared.
It's a circle with a radius of 5.
Oh, that's the radius. It looks like a diamond.
So pi times 5 squared. I could have written this a little bit better.
Okay.
The total area of the dartboard. What's the total area of the dartboard? 12 pi times 12 squared. The total area with pi times 12 squared times pi. The total area is this circle with radius 12. So then the probability of me hitting the bullseye, if I just hit it at any point at random, should be the ratio of the bullseye to the entire circle. I wrote my formulas like this for a reason. Notice that I'm divided by pi, I have multiplied by pi on top, multiplied by pi on bottom. There's a factor of pi in common on top and bottom. So when I reduce this fraction, those pi's actually cancel each other out in this case. So this should be the ratio of 25 to 144. And 25 out of 144 is what percentage? And with a calculator, you could check this out. It's got to be less than half.
Wait, no, it's actually no, it's probably
17.36. We'll truncate it there. 17.3 is fine. So I compare the two areas. I compare the areas, and the area of the bullseye compared to the area of the whole target is about 17.3%. And we do the same thing. We do the same thing for this little treasure hunting area. Notice that I don't have an exact area for this open field. It's just kind of like wobbly. So I'm going to have to estimate it. If the bird is equally likely to be anywhere in here, I want to compare the area of the success here is the wooded area, compared to the total area. So I need to be able to calculate these things. When you count boxes, this is a trapezoid with what? Base of 4 and 1. 9. So I have what? 16 plus 8. So what? 24 is this trapezoid. The wooded area has an area of 24 square units. The open field trapezoid formula is half of the height times the sum of the bases. I broke it into a 4x4 square and a 4x4 right angle. The open field we can estimate this area. Well, we can estimate this area maybe by looking at some like chunks. So this piece looks like it's about 9. This is about 2. This is about 2 squares. This is what, 1, 2, 3 and a half, maybe a little more than 4. There's an area. Area of about a little bit less than what, 4? Would you agree that those are not bad estimations, or? I mean, we're just estimating here. You could, as long if you said maybe like 3.5, I wouldn't argue with you. If you said like 2, I would definitely argue with you because there's clearly more than 2. I think it's pretty clear that there's probably more than 3 in here. Maybe not quite 4, but you could round if you wanted to round. That'd be okay. So in this case, the wooded area is what, 24. The total area is 24 plus 9 plus 2 plus 4, 6, 15, 39. The total area is approximately 39. So this bird that's kind of chilling out here is about what? 60. What is it? A 60.
64.
61.
61.
6.
About a 61.5% chance it's in this wooded area. If it's equally likely to be anywhere. We compare the areas.